So good evening everyone, and welcome to this course in this for this semester. Uh, the title of the course is Retrofitting and Rehabilitation of Civil Infrastructure, and I will be the TA for this course this semester. And basically, retrofitting or rehabilitation basically means the upgrading or re-strengthening or repairing of any infra of any structure without basically undergoing demolition. So basically this semester we will be dealing with how to repair a structure uh, which is basically an existing structure, and how to do it without demolition basically. So initially we will be studying how to retrofit the structure, which is basically an RC structure, that is reinforced concrete structure, and gradually we will expand our knowledge to solve or retrofit structures which are having FRP, that is fiber reinforced polymer, or steel structures, and also some special structures which are subjected to natural hazards such as earthquake. So let us start the discussion. And after the my way will be basically I will be revising the lectures for the entire week, and thereafter I will go for a solve go thereafter I will try to solve a few problems so that the concepts are cleared very much, so it will help you in further grasping the knowledge and enhancing the understanding. So let us start. So the first lecture basically, so we'll be basically starting from concrete structures. So the first week basically it is understanding the fundamentals of concrete, and what are the various types of damages, and what are the various aspects related to concrete structures which are required prerequisite for going for retrofitting. So let us start. So in this lecture, basically the introduction, we will basically be covering these concepts: introduction, need for retrofitting and rehabilitation of existing infrastructure, basic terminologies, brief description of the course, and the different modules. So if we see here, basically these are some of the new cutouts of the rise in the infrastructure domain sector, or the construction of new infrastructures, which is getting pace recently because of various schemes which have been launched by the Indian government. So along with that, there is also some of the news cutouts related to the deterioration of existing civil infrastructure, as can be seen here. So we can therefore say that the like there basically understanding the health of a structure or civil infrastructure is very much important as a civil engineer, and also it is very much important uh, for the basically the development of a nation at large. So because it is basically the basic requirement for a progress for measuring the progress of a country basically. So that's why the development is not possible without the role of infrastructure. So basically it is very much important to understand what is how to optimize the performance of a structure, how to understand how the deterioration occurs in any structure, and how to repair that in order to maximize the benefit. So these are some of the challenges for existing structure. One of the major challenges is the corrosion of RC structure. Apart from that, there are accidental explosions, and also overloaded vehicles, which basically create a negative effect on the pavements basically, that is the road infrastructure. So if we see basically, this is the ideal curve which basically represents the performance of any existing infrastructure as a function of service life, that is time. So if we see here, basically the performance actually gradually with time it deteriorates or declines. If we see, this is a trend line basically, and this is the reality of how the performance is behaving. So after a few like standard duration, the performance is basically deteriorates more than the trend line. Okay, and after undergoing a few maintenance, which is basically the repairment, so it is above the trend line, and again it deteriorates more. Okay, and again it is maintained, and finally it reaches the same point as per the trend line. So here, if we see that, if we see here, we will find that there is reduction in performance due to deterioration of existing structures, and there is decrease in durability and loss of service life as compared to the design life. So uh, basically, these are some of the reasons why there has been an increased emphasis on retrofitting and rehabilitation for the civil infrastructure, as can be again seen from these news cutouts from various newspapers. And people are also going for fiber reinforced polymer. So we'll be basically studying this in the upcoming classes. So how to retrofit using FRP composites. So now let us understand what is the basic requirement for retrofitting and rehabilitation. And thereafter, we will also understand a few basic terminologies related to it. So basically, uh, retrofitting and rehabilitation is required to improve the structural integrity and performance of an existing structure, to upgrade the functionality of a new structure, to upgrade an existing structure corresponding to the latest codal provisions, to restore the heritage value of a structure, to improve the durability and extend the service life of a structure, and to improve the appearance of a structure. So these are some of the basic needs for retrofitting and rehabilitation. And the benefits, they are quite it has numerous benefits. Basically, for the most important is the saving of financial resources. So it boosts the economy. So that's why it is part and parcel of the country's development, and that's why it is very much important. Okay, so firstly, the benefit is saving financial resources. Second is saving of natural resources. This is also one of the important parameter. Thirdly, it is saving of equipment and manpower resources. Fourthly, it is saving of user costs like delay, extra fuel cost, wear and tear of vehicles, inconvenience due to demolition of deteriorated structure and its reconstruction. And for fifthly, environmentally beneficial due to less dust, debris, waste disposal, and landfilling. And this it is beneficial because too much generation of all those may result basically in environmental hazard. Okay, it will basically create an environmental hazard, or it may have ecological significance. Okay, so in a negative way. So that's why it is important, or it is good if we can prevent this demolition, okay, if possible. So that is one of the important benefits of retrofitting and rehabilitation. So some of the basic terminologies related for this course. So let us understand those. So one is durability. So durability is basically the ability of a structure to resist the weathering actions, environmental effects, chemical attacks, abrasion, or any other process of deterioration. Second is inspection, which is basically understanding the current state of the structure. Third is evaluation, that is evaluating the present condition of the structure using necessary testing for making decision about further actions. Fourth is repair, measures to restore the integrity of the structure and improving its durability to reduce further distresses. Then maintenance. So that is basically process of keeping the present condition of the structure by regular inspection, evaluation, and repair. Restoration, that is necessary because that is basically the necessary measures which brings about the distressed structure in its original condition. So that is basically the deteriorated structure. Okay, so distress is a structure in the is a structure which is in physical deterioration, okay, or breaking down of a structure into smaller parts, and that can be due to a number of factors such as construction errors, chemical reactions, and natural processes. So we'll be going into more detail in the coming slides. So what is retrofitting? Retrofitting is basically strengthening measures to improve or upgrading the structural strength and performance, like load carrying capacity, ductility, etc. Okay, and rehabilitation is basically similar. Okay, so it is basically repair and strengthening like basically the measures associated with repair and strengthening for upgrading the distressed structure for an improved performance as compared to its original condition. So these were some of the basic terminologies. And let us go through the course outline. Okay, so which will be following in this 12 weeks. It is a 12-week course basically. So these are the basically the broad outlines of the course. So first module, so it is basically segregated into a few modules. Okay, so let us see the overall modules. So the basic module. So first module which we will be studying now, it is the deterioration of the concrete structures. It is module A. So some these are some of the pictures. Okay, so this is the flyover tragedy in a place called Mazarhat in West Bengal. So second module, which we'll be studying in upcoming classes, it will be basically on condition evaluation and testing. The third module, it will be on general repair and retrofitting of concrete structures. The fourth module, which will be basically on FRP composites and its characteristics. The fifth module, it will be on retrofitting of the existing structures using FRP composites. The sixth module, module F, it is basically concrete overlay for pavement rehabilitation. So we have also a week assigned for understanding how to repair and rehabilitate and retrofit the pavements. Okay, so then the next module will be on retrofitting of masonry structures. So masonry is basically any structure which is composed of stones, bricks, and also the cement or concrete as a binder. Okay, so then the next module will be on retrofitting of building structures damaged due to seismic events, as I said initially. So we'll be also studying how to retrofit buildings or structures undergoing earthquake events. Okay. Then next module will be retrofitting of special structures damaged due to seismic events. So this is example of a special structure. So basically this is a water tank. Okay. So how to retrofit this type of special structures also under earthquake events we will be studying. Then yeah, so this is the last module. So the last module will be on retrofitting of steel structures. Okay, so this is the last module. So we have J A B C D E F G H I J. So 10 modules we have. So basically in 12 weeks we will be covering 10 modules related to retrofitting and rehabilitation. So it will be a very exciting journey, and we will learn a lot in the process. So basically this was the lecture. Okay, the first lecture. So the summary we learned in this lecture was the need for retrofitting and rehabilitation, benefits of retrofitting and rehabilitation, basic terminologies, and a brief description of the courses with different modules. Okay, so the next lecture is on causes of deterioration in concrete structures. So in this lecture we will be basically covering the various causes, okay, which results in the deterioration of the concrete structures. So the different causes of deterioration in concrete structures, so they can be characterized into the 7 types. Okay, the various causes of deterioration. So one is the design or load associated distress. Distress is basically the physical deterioration. Second is the construction related distress. Third is foundation related distress. Fourth is material related distress. Fifth is distress due to weathering effects. Sixth is distress due to natural calamities. Seventh is distress due to accidents. So these are some of the causes of deterioration in concrete structures. So the first type of cause, that is design or load associated distress. So this can be due to various reasons. Okay, so it can be due to overloading. This can be due to overloading, as can be seen from the picture. It can be due to faulty or inadequate design. It can be due to change in functional performance, as can be seen in this bridge. Okay, then it can be due to increased loading, for example the flexural or bending cracks. Then it can be due to repeated loading, that is fatigue cracks. Okay, so fatigue is basically failure due to sustained or repetitive loading. Okay, so and so similar is this distress which is occurring due to sustained loading. So these are examples of design or load associated distress. Then there is construction related distress. So that is basically firstly, so construction related distress, it can be due to high water cement ratio. So this results into high capillary porosity. So capillary is basically capillary porosity basically it means the pores. Okay, which are in between basically the size of 3 nanometer to 30 micrometer. Okay, so the size of 3 nanometer to 30 micrometer pore size range, so that is basically called as a capillary pores. Okay, lesser than that we basically call them as gel pores. Okay, so they are lesser. Okay, we'll be discussing in coming slides. So higher water cement ratio that results into high capillary porosity and insufficient strength. It allows aggressive chemicals from environment to penetrate into the material, which will result into corrosion. Okay, and this is one of the reason for construction related distress. Second can be inadequate compaction or poorly graded aggregates, so as can be seen from the figure. So that can result into porous behavior due to the presence of air voids, and it can also reduce result in reduction of strength. Okay, so thirdly, a third factor can be inadequate curing. So due to inadequate curing or less than required curing, so that can result in shrinkage cracking. Okay, so shrinkage is basically the contraction in volume due to the loss of water. Okay, so that can be due to the loss of water, can be due to evaporation, it can be due to the sucking of water during hydration, or it can also be due to the unsaturated air. Okay, which is basically the taking out the water presence. So any loss of water basically results into volume contraction, and that is called shrinkage, and that results into cracking. So that can be due to inadequate curing. Okay, then your one more type of construction related distress can be shuttering joints. So the shuttering is basically the forma, okay, the formwork which is used during casting. And if this shuttering if these joints basically related to shuttering, if they are not slurry tight, okay, so there is leakage here. So that results into honeycombing in concrete due to bleeding. Okay, so bleeding is basically the water, okay, coming out of water. Okay, in concrete, bleeding is basically coming out of water. Okay, so that will again result into shrinkage also. So one more reason factor for construction related distress can be improper placement of reinforcement. So if the placement of reinforcement is not proper, okay, so if there is very less space between between the reinforcements, so that can result into poor compacted areas. Okay, so that means concrete mix is unable to reach these areas. Okay, so because it is so the space is very less, so the concrete mix will be unable to reach in these places or inside this, and that will result into poor compaction. Okay, and this will result into voids and inadequate strength. Okay, so it will have uh, honeycombing phenomenon also. Okay, so one more can be the inadequate cover thickness. So cover is basically the distance from the outer edge of the concrete to the reinforcement. Okay, so this distance is the cover. Okay, so if the cover thickness is inadequate or less than required, so it allows concrete and reinforcement to get affected by external environmental chemical attacks. Okay, and that will easily lead to corrosion. So that is one of the very prevalent or very serious problems nowadays. Okay, or it has been from time immemorial one of the very important topics in structural engineering, which is corrosion or durability. Then one more factor is improper alignment of formwork. So that is basically if this is the formwork, okay, and in this formwork there is one overload. Okay, so load which is like more than expected or desired, so that will result in a sagging. Okay, sagging is basically bending here, the flexure. So this will mean that there is a deflected shape of the bearer. So this is the bearer, okay, or the formwork. So the shuttering, so if there is a deflection here, so there is a sagging, so here it will result into hogging. Okay, so it will rise here. Okay, so that means the bearer, okay, the bearer lives here because of it got sagged here, and that means that a prop, okay, this is the prop which is supporting the bearer. So that it is a support, okay, during formwork, that is called prop. So this prop, if the bearer leaves, it will fall over. So this type of incident, if it happens, that will result into discontinuities on the surface of concrete, which will cause cracks. and there will be structural damage of concrete member. Okay, so these are some of the distresses related to construction. One more will be early removal of formwork. Okay, so that will result into overstressing of concrete and cracking, separation of material, or major failure. Then one more factor could be the poor quality of construction material. Okay, so as can be seen in the picture, so this will result into inadequate strength, allows easy attacks by external agencies, chemicals, environmental effects. Okay, so it will have some serious effects also because of the poor quality construction material. Okay, so these were some of the problems related to construction related distress. Then there can be foundation related problems also, which is causing distress. So one is the soil swelling and shrinkage. Okay, so that is mainly related to the geotechnical aspect. Okay, so we'll be studying all of them in detail in the coming classes. Okay, so this may result into various types of like there can be various factors due to which the foundation related problems can occur. One is soil swelling and shrinkage. One is differential settlement of the structure, which causes major cracks. Okay, so as can be seen here, so because of the differential settlement, there is a horizontal crack here. Okay, so because of the mechanics involved. Okay, so this is one of the differential settlement. So then there is foundational settlement due to erosion or inadequate soil consolidation. So that means if we see here, in this case there is uniform settlement, so settlement is uniform everywhere, so therefore there is no cracks. Okay, there are no cracks. If there is a tipping settlement means there is a small tilt. Okay, so if there is a small tilt or small overturning, then it is seen that mostly there will be no cracks. Okay, mostly it is without cracks. However, if there is a differential settlement, okay, so that differential settlement may occur because soil in this area has been eroded. So something like some sort of erosion may have occurred, and that may have resulted into differential settlement. So that means there will be cracks in this area. Okay, so the area where the erosion has occurred, there will be cracks. Okay, and if you see here, differential settlement, so if there is, say, one part of the house it has dry and loose soil, and the other part of the house it has wet and compacted soil, so okay, so that will result into differential settlement because the properties are different. Okay, properties of the soil are different, it is not homogeneous or isotropic. Okay, so that will result into foundation related problems. Okay, then there is material related distresses. So material related distresses can be like corrosion of reinforcement. Okay, so that will result into loss of reinforcement area, cracking and spalling of concrete. Then there is acid attack. Okay, so that will result into deterioration of concrete surface, reduction in strength. Okay, so we'll be discussing all of this in detail in the coming slides. After a few slides we'll be discussing. Then material related distresses can be also due to sulfate attack. So sulfate attack basically results into whitish appearance on surface due to deposition of salts, and this phenomenon is also called as efflorescence. Okay, and the loss of mass and reduction in strength because this has come from the interior. Okay, so that is basically type of leaching. Okay, so leaching is basically removal of a substance from a material. So from inside, if the salts such as calcium hydroxide and various silicates and sulfates, okay, so if they come out and they deposit here, so this is the basically leaching, so that results in the loss of mass, and also it creates cracks and it creates voids, so that results in the reduction in strength. And then there is again the alkali aggregate reaction. So this is basically, so this results into map cracking. So map cracking is basically cracking, map like cracking. Okay, so if you see the map is always, the shape is like this only. Maps, in maps, the shapes of states, countries, okay, basically are like that. So the cracking occurs in that pattern, so it is called map cracking, and this results in the increase in permeability, and also it finally results in the reduction in strength. Then there is distress due to weathering effects. Okay, so weathering is basically like the eroding effects of nature. Okay, so if we see here, say for example, there is a water flow over a soil or over a channel. Okay, over a channel or over a canal or over any structure. Okay, it can be any structure. So if there is water flow, and that water flow, okay, because of that water flow there can be cavitation. So cavitation is basically the weathering, okay, the eroding effect. And if in that flow there is circulating debris also, say for example this structure is a concrete structure, okay, so if water is flowing and over that structure and there is cavitation, okay, and if there is cavitation normally, and if there is debris also, okay, big or small debris, so that will cause additional abrasion damage. So here the damage was less, here it is much higher, okay. So that is basically the weathering in surface, it is basically abrasion, okay. So abrasion of surface, so it results into surface disintegration and reduction in cover thickness. And then there is temperature effect. So temperature basically in case of concrete, it results in blowing up due to thermal expansion, okay. So we'll be studying more detail in the coming slides. And then there is freezing and thawing action. So freezing is basically the water becoming ice, and thawing is basically again the ice converting into or melting into water. So that this phenomenon, this continuous freezing and thawing action, it can result into the volume increase due to freezing of water. And as we know, water always increases in its size about 9% when it freezes, okay, into ice. And that results into increase in capillary porosity, okay, and surface disintegration. So, so these were some of the weathering effects. Apart from then, that there is the seawater effect. Okay, so that results into abrasion and loss of material and corrosion of reinforcements. And there is also well alternate wetting and drying. So that can happen in any sea structure. Okay, which is partially submerged basically. So apart from that, there are distresses due to natural calamities such as earthquake, flood, storm. Okay, so this is example of funny cyclone. It occurred few years back, I think in 2021 or 20, something like that. And then there is tsunami. Okay, so in 2004, basically, one of the serious tsunami, a serious tsunami had occurred in our coastline in 2004. So then there are distresses due to accidents such as fire, blast, shock. Okay, so these are various types of distresses which can deteriorate a reinforced concrete structure. So that is like we have come to the end of this lecture. So in this lecture, the summary, which like basically if we summarize this lecture, we studied about the different causes of deterioration. So it can be due to design or load associated distress, construction related distress, foundation related distress, material related distress, distress due to weathering effects, distress due to natural calamities, distress due to accidents. Okay, so these are some of the distresses which causes the deterioration of reinforced concrete structure. So the next lecture, it will be basically understanding the material related distresses into more detail. Okay, so let us understand let us go into more detail the material distresses. So basically we'll be covering the following concepts. One is the corrosion and reinforcement, which is one of the serious events related to the deterioration, and also the acid attack in concrete. So what is corrosion in reinforced concrete? So that is basically it is a major problem, as we all know. So it is basically an electrochemical reaction. Okay, so it is an electrochemical reaction which is usually encountered when two dissimilar metals are in electrical contact in the presence of oxygen and moisture. So that is the general definition of corrosion. Okay, in case of steel, however, reinforcement, the same process of electrochemical reaction, it can take place in steel alone. Okay, we don't need two dissimilar metals. Okay, because of the differences in electrochemical potential. Okay, on the surface that forms anodic and cathodic regions. So basically, the difference in electrochemical potential in a rebar, okay, the differences that results in the differences in electrochemical potential on the surface of a steel rebar, that results in the formation of anodic and cathodic regions. Okay, so that is sufficient enough when it is connected with an electrolyte in the form of salt solution. So if it has oxygen water present, okay, so this difference in electrochemical potential is sufficient enough for forming anodic and cathodic regions in reinforcement, which will result into basically the corrosion. Okay, So this is the example of the corroded reinforcement. So so let us understand in detail what is the cause of corrosion. Okay. So if we see here, this is a concrete structure. So this is the surrounding concrete, and this is the reinforcement bar, rebar. So if you see the silver, the gray color, it is basically the interior rebar. And if you see this bold black lines, so that is basically the passivating film, okay, which is generated. Okay. So in concrete is very highly alkaline in nature, so it has a pH of 13. Okay. So if this value is less than 10, okay, so then the like basically we are converting it into more of a less alkaline environment, and that actually accelerates the process of corrosion. Okay, so we'll be studying more in the coming slides. So in concrete, the strongly alkaline, that is pH 13 nature of CaOH2, calcium hydroxide, prevents the corrosion of steel by the formation of a thin protective film of iron oxide. Okay, so, and its thickness of, it is having a thickness of few microns, or iron oxide. So this iron oxide is formed in the steel surface. Okay, because of the presence of calcium hydroxide. Okay, and this protection is termed as passivity. Okay, so the iron oxide basically it, due to the presence of calcium hydroxide, it has a thin protective layer of iron oxide on the steel surface, and this protection is termed as passivity. And because of the highly alkaline nature of calcium hydroxide, it does not have any effect on the iron oxide. Okay, so therefore it is very much stable in nature. As long as the film is intact, the steel surface is not exposed for reaction with oxygen and water. Okay, so because of the alkaline, high alkaline nature. However, as I told you, it has not been scientifically proven, but like it is yet to be scientifically proven. But any number, any pH number of less than 11 or 10, okay, so the passive iron oxide layer is destroyed. Okay, so any value less than 11, 10 or 9, the iron oxide layer is destroyed, and then the corrosion process starts. So if we see the fundamental corrosion reaction, okay, so the corrosion basically of steel is the reaction of iron with oxygen, okay, in presence of water to form its oxides and hydroxides. So basically the formation of hydroxides, oxides and hydroxides is basically nothing but the corrosion. Okay, so if we see generally, if we talk, the corrosion formula is Fe2O3.xH2O. Okay, that is ferric oxide. If we see here, ferrous oxide. So if we see here, this in case of rebar, so any formation of hydroxides is basically the corrosion, ferrous hydroxide and ferrous hydroxide, ferric hydroxide. So how it forms, let us see. In the case of anode, okay, in like in the portion of anode, basically the anodic reaction occurs. So anodic reaction is basically it oxidizes the iron. Okay, so from iron 2 electrons are released, so it becomes Fe2 plus. Okay, so that is oxidation. And here in the cathodic reaction, basically in the cathode, so the reduction occurs. Reduction is adding of electrons, okay, or negativity. So the 4 electrons, like 2 Fe 2 plus 4 E minus, so that 4 E minus, it comes and joins oxygen and water in the cathode region, and it forms 4 OH minus. So this OH minus and this Fe2 plus, so they combine and they form FeOH2. So that is nothing but the corrosion, and that has occurred, that has come through this portion. Okay, the Fe2 plus ion has come from this portion, so that's why it has resulted in mass loss in this anodic region. Okay, so the mass loss always basically occurs in the anodic region because the Fe2 plus is transferred from the anode only. Okay, so that is how that is basically the basic reaction of corrosion. Okay, so that is very interesting. Then, if we see here, the corrosion in the reinforcement of concrete, so that is basically of two types. One is the chloride-induced corrosion, and one is the carbonation-induced corrosion. Okay, and out of them, the chloride-induced corrosion is the main corrosion. Okay, so that is the main, the most dangerous form of corrosion. Carbonation is not that serious, and it also takes a lot of time. Okay, so the main corrosion, which is very much of serious concern, is the chloride induced corrosion. That is because it is mostly a localized phenomenon. Okay, so because it is a localized corrosion, so the intensity is quite high. Okay, so that's why it is of various it is of very high significance in research. Okay, so even in my PhD also I am working on this topic only. And apart from that, the carbonation induced corrosion, it is basically a uniform corrosion. So it is uniform because it is mainly dependent on carbon dioxide gas. So that as it is diffused everywhere, so it is more of a uniform phenomenon. Okay, so these are some of the examples of corrosion in reinforcement. So the chloride induced corrosion basically it happens when the basically the concrete is, so it is mostly related with permeability. When the concrete is permeable, the water and chloride penetrate and reach up to the reinforcement. So there is intrusion of chloride ions. Okay, uh, there is an intrusion of chloride ions towards the reinforcement. So these chloride ions surrounding the reinforcement react with steel to form FeCl2. Okay, so here basically like what is the difference between the chloride induced corrosion and the carbonation induced corrosion? Okay, so the carbonation induced corrosion, it basically follows the normal process, like the normal process of corrosion. Okay, so this happens when basically it happens when the pH falls below 11. Okay, so when pH falls below 11 or 10, this type of corrosion occurs. Okay, but the chloride induced corrosion, it does not need the pH value to be less than 11. Okay, so why it is? Because when the iron the chloride ions come basically, so because of it having a more electrostatic potential. Okay, so it can basically, as we studied here, it basically has a, the rebar basically has a layer of iron oxide. Okay, so when the iron oxide like when the chloride ion reacts with that iron oxide, so it can directly displace the oxide. Okay, it can displace the oxide and it can form FeCl2. So it does not need the pH to fall below 11. Okay, so it can, because of its higher electrostatic potential, it can displace the oxide, so it forms FeCl2 directly. There is no question of pH. Okay, so this FeCl2, so this change, okay, so this reaction that is basically happen in the that happens in the anode. Okay, anodic reaction. So here the corrosion product also forms, as I told you, and this FeCl2 then reacts with water. Okay, and it forms HCl. So that happens in this region. Okay, so this FeCl2 then like after it is formed, it goes here. Okay, so this picture is basically a little bit exaggerated. Okay, so here basically the anode and cathode will be nearby only, so it is too much exaggerated here. So basically here, after FeCl2 is formed, so it goes to the cathodic region. Okay, and then it reacts with water. Okay, as can be seen here, and it forms HCl and FeOH2. So this FeOH2 is basically the corrosion product. Okay, so that is this formation. Okay, so the ferrous hydroxide, it is this. Okay, so that is basically the anode like the corrosion product, ferrous hydroxide and ferric hydroxide. And the problem, like the seriousness of this chloride induced corrosion is that there is a formation of HCl. Okay, so in the normal corrosion there is no formation of other byproducts. Okay, only ferrous hydroxide and ferric hydroxide. But in the chloride induced corrosion, apart from ferrous hydroxide, there is a formation of what hydrochloric acid, HCl. Okay, so this is a very dangerous like this is the reason for its few like the it results in its propagation, the corrosion propagation. Okay, so that is because of the general process of corrosion. So what happens, because it is a strong acid, so it will easily make the pH fall below 11 or 10. Okay, so that will result in the depassivation. That this passivation layer of iron oxide, it basically gets dissolved in the basically the concrete. Okay, the moisture, oxygen, and the low pH, so that is a recipe for dissolution of the passivation layer of iron oxide. So that is basically what it is written. So HCl destroys the passive protective film on steel, thus resulting into corrosion on the steel surface. So once if the chloride ions can attack the FeO, okay, and if it forms FeCl2, and that ultimately forms HCl, so then it will like it is a chain reaction. Okay, it is a fusion basically a fusion reaction, so it will go on and on and on. Okay, so that is like the initial it does not need pH, but after it FeCl2 is formed, so then the hydrochloric acid will easily lower the pH. Okay, so that is the reason why the chloride induced corrosion is such a grave concern in existing structure, and most of the structures, main reason for failure of deterioration of structure is the chloride induced corrosion. So as you can see here, the electron flows here, okay, the two electrons, it forms into hydroxide, and then it joins the Fe2 plus, results in ferrous hydroxide, okay, and along with the production of HCl. And anodic reaction, corrosion product forms here, and cathodic reaction, hydroxide ions produced. So that is basically the chloride induced corrosion. And now the carbonation induced corrosion, so that is basically it is similar to the normal corrosion process. So it is a electrochemical corrosion process. So here if you see, the pH in the anode, as I told you, it falls into less than 9, okay. So there is no clear scientifically proven value of the pH below which the carbonation, the corrosion occurs. It can be less than 11, it can be less than 10, it can be less than 9, okay. So around 10 it is generally considered, okay. So here it is the sound concrete, okay, it is having a pH of greater than 13, okay. So in anode, pH comes less than 9, so that results in the general process of corrosion. And for corrosion to occur, the following are required: the rebar has become depassivated by carbonation, that is pH less than 9 at crack, okay, that is anode, okay. So here the crack has occurred, okay, so that is basically due to the cracking has basically occurred due to the formation of the rusting products, okay. So these rust products basically, and which is basically the ferrous hydroxide, and also due to the formation of calcium carbonate also, okay, because it is occupying extra space. So the oxygen, O2 and water, H2 are available at cathode, and that is the similar reaction, and concrete has adequate moisture content. So calcium hydroxide plus carbon dioxide, it forms calcium carbonate plus water. So that is basically the intrusion of carbon dioxide, and after that formation, the normal process of corrosion follows. So the ingress of CO2 from atmosphere through surface cracks and consumption of calcium hydroxide, lowering of pH of surrounding concrete, destabilization of passivating film, formation of carbonates and bicarbonates, and deposition on steel surface, cracking of concrete, reinforcement is exposed, and corrosion takes place in presence of water and oxygen. So this is the basically this is a sketch of the degradation zones of a carbonated concrete structure taken from a literature. So if you see here, this is a concrete covered depth, okay. So this is a carbonated concrete which is having a pH of 9, and this is the uncarbonated concrete of 13, and this is the carbonation front, okay. So this is the, like, it is the intermediate layer between the carbonated and uncarbonated regions, and this is the depth of carbonation, and the external surface of the structural element is contaminated, and a transition zone called the carbonation front. So the intermediate zone is called the carbonation front, and there is a drop in pH in the concrete cover due to carbonation. So overall the pH has dropped if we see the equivalent value, and this is the internal zone of the element, which is basically the not contaminated sector. So this is basically the sketch of the carbon induced corrosion. So there is also, as you can see, the figure here of corroded reinforcement. Maybe it has been degraded due to carbonation. So there is a diagram also. It's called the Purbai diagram of iron corrosion, passivity, and immunity zone. Okay. So from literature it has been taken. So E naught value, it basically represents the corrosion potential. So the Fe2 plus, which is basically the main agent, okay, the main radical which results into corrosion. So if we it has a corrosion potential between minus 0.4 to 0.8, okay, and volt, okay, minus 0.4 to 0.8 volt. And if you see here, the this is the basically the corrosion zone, okay. So if you see, the zone occurs for a pH less than 9, okay, above that there is no issue, okay. So how the corrosion actually affects the structure, okay. So there basically it is very simple. So the formation of rust, okay, and crack initiation. So what happens, this is a sound specimen of steel rebar and concrete, that is reinforced concrete. So after corrosion there is a formation of rust, okay. So this is the rust formation on surface of steel, and that results in creation of external pressure, okay. So that means it induces some tensile stress on the concrete, okay, nearby concrete. And when this stress, okay, is basically the tensile stress when it is higher than the tensile strength of concrete. So tensile strength of concrete is basically the flexural strength, which is basically points around like it is about the flexural strength, which is around zero point 0.7 root FCK. Okay, so zero point 0.7 of square root of FCK. So when the strength of the tensile stress produced by this rust formation, it increases, it is higher than the zero point 0.7 root FCK value. So then there is this formation of cracks. Okay, and that is due because the concrete is subjected to internal expansive pressure, which is the tensile stress. So, what are the effects of corrosion? There is loss of cross-sectional area of steel, reduction of tensile capacity of members. Corrosion products are more voluminous than the parent metals, formed and deposited on the affected steel surface. It causes the surrounding concrete to experience internal expansive pressure, as can be seen here. Okay, and the development of longitudinal cracks and concrete, consequently spalling, depending upon depth of cover, spacing, and diameter of bars. So these are some of the factors, and as can be seen in the figure also. And corrosion induced cracks provide easy access to deleterious materials, that is harmful materials, from outside environment, thus accelerates its damage. Okay, so you can see this is a pictorial representation of that, the entire description of effects of corrosion. So before corrosion it was a sound specimen. So results of corrosion, there is a buildup of corrosion products. This upon further corrosion, there is surface cracks and stains. Okay, as can be seen. And finally there is eventually spalling. Okay, spalling is basically the cracking and the it is basically the delaminate, it is called delamination, when you can remove the chunks of concrete. Okay, so or it is also called it is also known as exfoliation. Okay, so you can layer the surface, okay, due to cracking. So this eventually leads to spalling or cracking, and it corrodes the bar exposed. Okay, so it is finally it is in a very deteriorated and damaged condition. How to prevent corrosion? So that can be done using these methods. One is impermeable concrete surface, so making it impermeable, the surface of concrete. Second is having adequate cover depth. Third is concrete with alkaline atmosphere. It prevents corrosion even in presence of large quantity of chloride. So that's why the pH should be higher or more than 13. Okay, equal to or higher than 13. So then we can have dry atmosphere, that is relative humidity below 40%. uh, Even in fully submerged concrete there is less corrosion except water with entrained air. Then because again then there will be intrusion. Okay, like there will be intrusion of chloride and all those this acids and metal, the chemicals basically. And then we can use go for use of corrosion inhibiting admixtures. Okay, reducing admixtures, such as increasing the chloride threshold level to cause depassivation. Okay, so for example we can take calcium nitrate. Okay, so it will increase the chloride threshold level to cause depassivation. And also we can go for epoxy coating reinforcement. Okay, so that will also basically provide an extra layer of protection. So then let us come to acid attack. Okay, so that was all about corrosion. Now let us go to acid attack in concrete. So that is found in areas of industrial activities, food processing plants, floors of dairies, chimneys, etc., due to the formation of lactic and acetic acids. In damp conditions, sulfur dioxide and carbon dioxide and some other gases present in atmosphere form sulfuric acid, carbonic acid, etc., which attack concrete by dissolving and removing a part. Domestic sewage, alkaline in nature, causes deterioration of concrete sewer pipes when sulfur compounds in the sewage are reduced by anaerobic bacteria to H2S, which after oxidation produces sulfuric acid. So that is basically the mechanism, which is how the acid attack occurs. And this is an example, pictorial example of the concrete under acid attack. So the concrete is also attacked by water containing free carbon dioxide. Okay, so that is similar to the carbonation. Okay, and the carbonation corrosion. Okay, so it is attacked by water containing free carbon dioxide in concentrations of at least 15 to 60 ppm. And due to this attack, some parts of the hydrated cement paste are disintegrated and leave a soft and weak mass. Degree of attack increases with acidity of the solution. Okay, because of the the corrosion basically. And water with pH is pH less than 6.5 is susceptible, and pH with less than 4.4 there severe acid attack occurs. Okay. The rate of acid attack also depends on the ability of hydrogen ions to diffuse through the CSH gel after calcium hydroxide has been dissolved and leached out. Okay, so as I told you initially, so because of acid attack, there is removal of any substance, okay, any chemical or any mineral or compound from or molecule from the concrete inside concrete. This is called basically the leaching process. Okay, so the so this because of the removal, so after that the ability of hydrogen also diffuse the CSH gel. Okay, so that also may result into disintegration. Okay, so that basically damages the concrete and reduces its strength. Okay, so these are some of the reactions which occur in acid attack in concrete. So because of nitric acid, sulfuric acid, carbonic acid, hydrochloric acid, and acetic acid. So these are the reactions for properly understanding the mechanism. So how to resist this acid attack? So this resistance to acid attack can be achieved using protective layers as surface treatment, epoxy resin, coal tar, rubber or bituminous paints, use of antibacterial cement containing some toxic material, impermeability of the surface. So these are some of the standard ways to resist acid attack. So, if we summarize this lecture, so we studied the material related distresses. So, firstly, we went through the corrosion and steel reinforcement. What were the causes of corrosion? We understood in more detail about the chloride and carbonation induced corrosion, the effect of corrosion, prevention of corrosion, and then went to the acid attack. Okay, we studied the acid attack in concrete. What were the causes of acid attack, effect of acid attack, prevention of acid attack. Okay, so we went through causes, effect, and prevention. So that was all about the last lecture. So now the next lecture also we will be continuing the material related distresses. So in this lecture we'll be covering the sulfate. We'll be basically covering the sulfate attack in concrete and the alkali aggregate reaction AAR in concrete. So what is sulfate attack? So hardened concrete when it becomes permeable, it may be attacked by sulfates from external sources. So typical sulfate sources can be groundwater, okay, that contains sodium sulfates of sodium, potassium, magnesium, calcium, seawater, soil, free water. Okay, so these are typically some of the sulfate sources. Chemical reaction resulting into increase in volume and disintegration of material, and these are whitish in appearance. Okay, so that is also called efflorescence, and the damage starts at the edges and corners, and it's followed by cracking and spalling of concrete. Okay, so this is basically the example of sulfate attack. So the external sulfate attack, okay, so there are three reaction steps. One is the chemical reaction, one is the sulfate from external, it has gone to internal. So the relevant factor for that is permeability. Okay, so from external it has included or come into the it has penetrated inside internally. So that is permeability is a relevant factor. Then there is a reaction between calcium hydroxide and the alkali metal, alkali element, like sulfate sources which are because of like the alkali of uh, sulfates of any alkali source. Okay, so that also results. So basically this sodium sulfate, it can be due to the groundwater water, like it is coming from soil water or any type of like any of these sources. So it reacts with calcium hydroxide and it forms calcium sulfate. Okay, so that is basically gypsum. Okay, calcium sulfate dihydrate, so it is gypsum, and so that again results into sulfate attack. So that is basically dependent on the calcium hydroxide content. And apart from that, there is also due to the chemical reaction occurring due to as a result of attringite. Okay, so because of attringite also, the too much attringite also results in the external sulfate attack. And for this the relevant factor is the C3A content. So that is the this content. Okay, so tricalcium aluminate. So more is the C3A content, greater will be the attringite formation. Okay, so that's why this is also responsible. And the sources can be seawater, soil, groundwater, effluents from furnaces that use high sulfur fuels, decay of organic matter mixed in marshes, shallow lakes, mining pits, sewer pipes. Okay, so these are some of the sources. And this is the attringite needle. So this formation, this has been depicted here, and that leads to expansion and cracking of concrete. Okay, and this is the example of spalling due to sulfate attack. So the internal sulfate attack, okay, so that is basically external. Now let us come to internal. Internal sulfate attack, it affects internally without any contribution from the environment. During mixing process, the use of sulfate rich aggregates, excess addition of gypsum, okay. So this results in the delayed attringite formation, DEF. So this arises when concrete exposed to temperature that causes decomposition of attringite and again exposed to moist condition. So this results in the reformation of attringite. And then precast concrete also, the concrete cured in autoclave. Autoclave is basically when curing is done at a high temperature and high pressure, or at elevated temperature. So elevated temperature is only elevated temperature, no, not high pressure. But autoclave, both elevated temperature as well as high pressure. Okay. And steam curing, so steam curing is basically this only, elevated temperature. Okay, and non, but not high pressure. Okay, and or in the case of massive structures. So these are some of the places where the internal sulfate attack occurs. And due to the DEF, there is damage in concrete. So attringite, usually in the form of massive crystals and they're expansive in nature. Aggregate is no longer contributing to concrete strength since it is effectively detached from the cement paste. So here if you see damage in concrete due to DEF, the cement paste is expanded and a gap is formed between the aggregate and the cement paste. So this is the gap basically. These gaps become filled with attringite because uh, they expand and they also result in cracking. Okay, so that is the way how the deterioration occurs. And here if you see these are some of the figures taken from literature, which shows the expansion and compressive strength changes with time. Okay, as a result of sulfate attack. Okay, so if you see here the expansion, basically this is the expansion, so it increases with time. Okay, so as per one literature, it increases like one literature has found that the change in specimen dimension and compressive strength versus time, so it has found that with time the expansion increases. Similar was also found in one more literature. Okay, similarly. Okay, so it has taken less time and it has taken more time, but it is increasing. And if we see the strength, okay, strength, it reduces. Okay, it reduces with time. And the dynamic modulus also, the dynamic modulus, that is basically the static modulus divided by 1 plus theta. Okay, theta is the creepage, if you remember. So the dynamic modulus, so it is constant up to 60 to 70 days, and then it has a very abrupt, like significant reduction. Okay, so it like the change is very rapid. Okay, so the extent of sulfate attack depends on the concentration of sulfates and permeability of concrete. So what are the effects of sulfate attack? So the concrete affected by sulfate attack, it has various effects such as higher permeability of concrete, which leads to leaching of calcium hydroxide. And then there is efflorescence, which I talked about. It is the formation and deposition of this calcium carbonate due to the reaction of calcium hydroxide with CO2, and it has a whitish appearance. Then there are deposition of salts in the form of carbonates and bicarbonates on the surface and within the pores of masonry, mortar or plaster when the salt solution evaporates. Okay, so these are the effects. And how to provide resistance to the sulfate attack? It is through use of sulfate resistant cement, which is having low C3A content in areas having high sulfate containing soils, groundwater and seawater. Use of fly ash blast furnace slag as a replacement of some amount of cement, that is therefore having less CaOH2 formation, because that was also one of the reasons. Okay, if you see here CaOH2 content. Then lesser use of sulfate rich aggregates and lower water cement ratio, which should not exceed 0.5, because more water means more chance of reaction of sulfates, okay, happening. Apart from the more gel pores, sorry, capillary pores, which can result into much like which can cause a problem of astringent like expanding and resulting in more like making a layer again, trying to make a damage by increasing the gap basically, okay, because of its expansive nature. So these are some of the ways to resist the sulfate attack. So now let us go to one more phenomenon, which is the alkali aggregate reaction in concrete. So concrete, as we all know, it is a two-phase composite, okay. One is the aggregate phase and the second is the cement matrix phase. So basically it is the mortar phase, okay. So the aggregate phase is generally inactive and does not react with the cement content. The aggregates contain a large amount of silica, SiO2. The SiO bond is one of the most stable bonds, reason of inertness of most aggregates. Certain aggregates are, however, not inert, okay, and they react aggressively with the pore solution. It is termed as alkali aggregate reaction, AAR. So this is an example of concrete affected by alkali aggregate reaction. So AAR is a reaction between reactive minerals present in aggregates and alkali metals, sodium and potassium, present in the pore solution formed during the hydration of cement. Okay, so these alkali metals can be like present in small quantities in the raw materials of OPC and remain as part of OPC. And the reacted concrete results in map cracking. Okay, so cracks as in the shape of maps, increase in permeability, reduction in strength, less durability. So the map cracking pattern caused by alkali carbonate reactivity. So as you can see here, so if we see, like if we schematically depict the process, so the reactive silica or silicate in the aggregate, it reacts with the alkali in the cement, okay. So therefore a gel forms on the aggregate surface when sufficient moisture is present. So the swelling takes place, okay, and it causes surrounding concrete to develop tensile and compressive stresses, and this results in expansion and map cracking in concrete, as can be seen here. So there is alkali silica reaction, alkali silicate reaction, and alkali carbonate reaction in the alkali aggregate reaction. And here if we see here, so these siloxane bonds, okay, at the surface of silica, so as water is absorbed into the gel, it swells considerably. The the attack of siloxane bonds continues till the outer layer of the gel breaks down completely, okay. So this they basically attack, okay, so they attack the gel, okay, and it breaks the outer layer, and it releases silicate groups into solution. So these are the silicate groups. If you see, these are the silicate groups released into the solution, and the silicate groups removed from the gel are likely to be involved rapidly in reactions between calcium ions to form CSH gel, okay. So this is in a way also how the geopolymerization also occurs, okay. So but here it is negative, there it is positive, okay. So like that is the like that way it results in this swelling, and that swelling results in the tensile compressive stresses, okay. So because of its expansive nature, increase in volume, and that results in map cracking. So this is basically the alkali aggregate reactions involved. Basically the alkali carbonate reactions have been shown here. So the dolomite reacts with the hydroxide of sodium potassium, resulting in brucite, that is magnesium hydroxide and calcite, and magnesite, which is magnesium carbonates, also result in brucite and also calcium carbonate, okay. This is basically the this one the equations involved. And expansion is due to expansive clay particles or microscopic quartz particles, that is SiO2 particles, present with carbonate mineral matrix. Expansion is due to the precipitation of brucite, this it is this in confined spaces, okay. So that is all about alkali carbonate reaction. And what is alkali silicate reaction? Reactive minerals with a layered phyllosilicate structure present in aggregates may exfoliate, that is it may result in delamination or the spalling basically, okay, under high pH condition, permitting water to occupy the space between the layers. So it basically results in layering, okay. So gel is formed that results into expansion and consequently cracking, okay. So the alkali aggregate reaction basically depends on the presence of reactive aggregates, porosity of aggregates, quantities of alkalis in cement, availability of water in the cement paste, and permeability of cement paste. So these are some of the factors. And if you can see here, this is a pictorial representation of the fragments breaking out of the surface. Okay, that is the pop outs. Okay, that is occurring because of the alkali aggregate reaction. So what are the implications of alkali aggregate reaction? So it is a slow process. It starts at the surface of aggregates and gradually proceeds within the entire material. Cracking of surface promotes ingress of water, harmful gases and deleterious materials. Additional strain in reinforcing steel, reduction in strength due to cracking, aesthetically unacceptable. So how to resist this? So by using firstly the non-reactive aggregates, mixing of reactive and non-reactive aggregates, use of low alkali cement, use of SCM like fly ash, slag, etc. Preventing water permeation by applying suitable coating on existing concrete. So these are some of the ways to resist alkali aggregate reaction. So to summarize this lecture, we basically in this lecture studied the material related, we continued studying material related distresses. Like firstly we studied the sulfate attack in concrete. So we studied the causes of sulfate attack, the external and internal types of sulfate attack, the effects of sulfate attack and the resistance of sulfate attack. And then we extended our discussion to alkali aggregate reaction in concrete. There we basically studied the causes, implications and resistance of AAR. Okay, so the next lecture it is on other distresses in concrete. So here we will cover the following concepts. First is the freezing and thawing. Second is the thermal effect. Third is the shrinkage, and fourth is creep. So what is freezing and thawing in concrete? So if we all know, like what happens basically is the normal water freezes at 0 degree centigrade under the atmospheric pressure. So when the water freezes, there is, as per literature, there is a increase in volume of water by about 9% when it converts into ice. Okay, so the volume increases 9%. In concrete, the water solution, the water or solution of various salts within capillary pores freezes at temperature less than 0 degree centigrade. So normally water freezes at 0 degree centigrade, but inside the capillary pores the water which is present in solution of various salts. Okay, so that basically freezes in less than 0 degree centigrade. So that is basically the lowering of freezing point. Okay, so the lowering of freezing point is occurring. Okay, so in chemistry there is a concept by which this phenomenon is occurring, and that's why we also basically sprinkle salt in the snowy places. Okay, when we want to basically reduce the snow in roads and all, we sprinkle. Okay, so that the freezing point basically lowers. Okay, so that is happening here. So in concrete the water freezes at temperature less than 0 degree centigrade, and it has been found that lesser the size of capillary pores, lower is the freezing point of water within it. Okay, so lesser is the capillary pore size, lesser is the capillary pore size, lower is the freezing point of water within it. And most freezing takes place in capillary pores. That is because the gel pores are too small for freezing. So capillary pores, as I told you, it is between 3 nanometer to 30 micrometer range, and gel pores are even lesser than 3 nanometer. So it is too small for freezing to occur. Okay, so most freezing takes place in capillary pores. And when there is gel water and ice, okay, both ice and gel water present in capillary pores, that also results in a thermodynamic imbalance. Okay, so that also results in stress. Okay, so that is the effect of freezing and thawing. And here we can see the concrete getting affected by freezing and thawing. So with decrease in temperature, freezing of water occurs gradually with some amount of unfrozen water in the capillary pores. So this unfrozen water experiences hydraulic pressure by the expanding volume of ice. Okay, because the other frozen water basically it has expanded, and that has resulted into the stress. Okay, in the unfrozen part. And this pressure, if not relieved, it can result into internal tensile stresses, and that can cause localized failure. And in saturated concrete, as there is no voids, the unfrozen water has no space to move, and that results into internal stresses, which when exceeds the strength of cement paste, the damage occurs. Okay, so as we can see here, concrete surface disintegration due to freezing and thawing. Okay, so this is a representation of that. Now Freezing and thawing basically depends on the degree of saturation and the pore structure of cement paste. Okay, so if you see here how it can have a very terrible effect on pavement basically. So if we see here the water above pavement, when say for example it was like the water during night time it was frozen. Okay, so during daytime the ice, like this water has it has melt. Okay, this which was in the form of ice, it melted. The ice melted in warm weather, filling the cracks with water. Okay, so that then as temperature again dropped, okay, water freezed. Okay, so this is basically a phenomenon in cold areas basically. So water freeze there, and because the volume of freezing water is more, it expanded, and that resulted in the cracking of surface. Okay, so did resulted in cracking of surface. And this cracking, okay, so this cracking was also further exaggerated when the when there was movement of vehicles. Okay, so the traffic further broke up the surface. Okay, so this double effect, double damage. And if you see here pictorially the mechanism, so melting water goes into capillary pores, okay, after upon melting. And then melting of so this is the melting of snow and ice. It after melting it goes into capillary pores, and then water freezes and tries to expand, and that results in the creation of voids. Okay, so that is the example, that is the mechanism basically. And if we see here how the how it affects rocks, so the water collects in rock crack, then it freezes and expands, forcing cracks to widen. Then the ice thaws. Okay, so thaws means it again melts, contracts, and water goes deeper into cracks again. And then repeated expansion and contraction causes further cracks until complete breakage. Okay, so that is how the freezing and thawing effect in rocks occur. And a concrete bridge parapet wall exhibits severe deterioration caused by repeated freezing and thawing cycles, as can be seen here. So, like, what is the effect of freezing and thawing phenomenon? Okay, so the repeated cycles of freezing and thawing that results into disintegration of pore structure, that results into pop out and surface scaling. Okay, so that is the developing of layers due to gradual disintegration. And how to resist this? This is firstly by using dry concrete. Secondly, having a degree of saturation which is 80 less than 80 to 90%, so that there is some voids, okay, that can be like that can be left for the freezing water. Okay, because the ice will like the water will expand by 9%. Okay, so if it is less than 90%, so it has the 10% left. And there like one of the best ways is also through air, and like using some air entraining agents. Okay, so air entrainment can also be a way forward. So uh, basically we can go for some admixtures basically. And like what is the air entrainment process? So it is intentionally entraining air or inducing air bubbles in concrete by suitable admixture or additives to provide resistance against alternate freezing and thawing. The admixture mixed with water rapidly produces discrete air bubble cavities and or finely divided stable foams. Okay, so they basically result into foam cavities, bubble cavities, and they have size of air voids about 0.05 to 1.25 mm. Okay, and these additives interground or grounded together with cement. Okay, they are like we take about 0.005% to 0.05% by mass. Okay, which of cement. And the minimum volume of voids is 9% of the volume of mortar, evenly distributed. So 9% is because as per literature 9% increase in the volume of water is found when it converts into ice. Okay, and it should not have harmful effects on concrete, obviously, because it will otherwise have some other side effects. So the presence of adjacent air voids and empty capillary pores allow a relief of hydraulic pressure by the flow of water into these spaces. Extent of stress relief depends upon rate of freezing, permeability of cement paste, and length of path to travel by water. The air entraining agents, they can be any animal or vegetable oils and fats, natural wood resins, alkali salts of sulfated or sulfonated organic compounds. So it can be of various types. Okay, so the basic idea is to create the bubbles, air bubbles, okay, of about 1 mm size, okay. So these are some of the, this is the example of introduction of air voids into concrete, okay. So if we pictorially, schematically see how the air entrainment can like positively affect the freezing and thawing action. So resistance to freezing and thawing by air entrainment. So these are the air entraining cavities, okay, the voids, and these are the, basically this is the capillary pores basically, okay. So and they are basically interconnected, okay. So if we see here, as temperature drops, pores from air entrainment allow the unfrozen water. So this is basically the unfrozen water, okay. So this is the frozen water, this is the blue color basically is the unfrozen water, the white color is basically the frozen water, okay. So the unfrozen water, when the temperature drops, pores from air entrainment allow the unfrozen water a place to go, okay, through the capillary pores. During freezing, water in capillary pores expands, okay. So in the capillary pores, the water expands during freezing, and because of the formation of ice, and under pressure water is pushed, the unfrozen water, it is pushed into the air entrainment process. As you can see, all are covered with blue, and air entrainment pores, and not crack the concrete. So because they are filled up in the air entrainment pores, so they will not they will reduce the cracking, okay. So they will not result in cracking. So that is a way through which we can mitigate the effect of freezing and thawing action. So next, let us come to the next topic, that is thermal effect in concrete. So basically concrete has a positive coefficient of thermal expansion, which is basically the value of alpha, okay. The thermal movement caused by temperature changes from minus 30 degree centigrade to plus 65 degrees centigrade. The cement paste and aggregates, basically they have dissimilar thermal properties. The aggregate basically has a higher thermal coefficient, and it restrains the thermal movement of the cement paste, okay. And it has been found that higher the volume of aggregates, lower is the thermal coefficient of concrete. So if you see here, it is opposite, okay. So higher concrete has higher thermal coefficient, but if the volume of aggregates have higher volume, sorry, aggregates have higher thermal coefficient, but if the volume of aggregates are higher, the thermal coefficient of concrete is low. So this is because if we see in concrete, basically the aggregate, okay, the aggregate is around 40 to 50%, okay. Generally it lies between 40 to 50% in volume, and the cement is around sorry, the sand is around 20 to 30%, and cement generally lies around 10 to 20%, and rest is water and void, okay. So the aggregate is around 40 to 50%, so it is less than half, okay. So if we increase the volume of aggregate, so more will be the volume of non-aggregate, okay. So that means non-aggregate will have a uh, it will have a lesser thermal coefficient, because aggregate is a higher, okay. So that means the concrete thermal coefficient, which is having which is basically having a larger volume of non-aggregate, so it will be basically lower, because the volume of non-aggregate is lower, okay, and it is having a higher volume. So that's why with the higher volume of aggregate, there is lower thermal coefficient of concrete. So this is an example of crack due to temperature effect. And if we see how the temperature effect occurs in concrete, so there are two types of variation. One is daily variation and one is seasonal variation. So if you see daily variation, the curling stress occurs. So if we see what is that, so in night, the upper surface of concrete is cooler and the lower surface is warmer. And in day, the upper surface is warmer because of sun, and the lower surface is cooler, right? So what happens is, during day, because the upper surface is warmer, here the compression occurs, okay, and that results into sagging, okay. So in the night it is sagged, okay, and during, because it is sagged, okay, it is cool, so here the expansion occurs, okay. So as we just saw in water, in the case of water, during if it is cool, the volume increases, okay, or it expands, and in a high temperature or warm condition, the volume contracts or it shrinks, okay. So during cooling time, it undergoes tension, and because it undergoes tension, during day it again hogs, okay. So hogging results hogging results into sagging, and sagging results into hogging, okay. So that's why it is opposite. Okay, so in cooling, it undergoes tension and it changes its shape, and again at daytime it becomes warmer, it contracts, compression, and it again sinks. Okay, and similar in the lower part. Okay, so to address the and also in the case of season, this is the daily variation. In the seasonal variation, there is resistance to change in length. Okay, so which results into frictional stress. So that is basically, if we consider this as the original length, during summer it will increase in the this one it will increase in uh, its length. Okay, so delta t, alpha L delta. So if we see here, both are opposite. Okay, so in the case of curling stress, the warm results in compression. Okay, and cool results in tension. However, in the case of your this one, in the case of seasonal variation, the that is basically in the width as compared to the length. Okay, the summer will really the summer season will basically result in the increase in length. Okay, that is alpha L delta T, and the winter will it will result basically in shrinking. Okay, so that is the opposite variation. And that variation, it basically tries to resist. Okay, and that is the reason why the frictional stress is created. So to address the thermal effect, expansion joint and contraction joints are provided between concrete slabs, so so that they have that adequate space for allowance of that variation. So if we don't have that space, okay, if we don't have that joint, so it results in this type of behavior. Okay, so the concrete blow up in concrete pavement. Okay, and then there is curling measurement in concrete pavement. So if you see here, there is little bit of curling, and if we see, there is a variation of temperature across depth of concrete slab. So more we go to the near of the surface, the temperature increases. Okay, now let us go to the next topic, which is shrinkage in concrete. So that is the non-load associated deformation in concrete. The volume change in concrete when partly or wholly restrained induced stresses. When these stresses exceeds the tensile strength, then the concrete cracks. Caused by loss of water due to evaporation, hydration of cement, carbonation at different stages. Expressed as linear strain, millimeter, that is in terms of millimeter per millimeter. Generally, it ranges from 15 to 10 to the power minus 6 to 1600 into 10 to the power minus 6. And this is an example of shrinkage crack. Okay, so there are basically four types of shrinkage. One is autogenous shrinkage, one is plastic shrinkage, one is drying shrinkage, and one is carbonation shrinkage. So what is autogenous shrinkage? It occurs when there is loss of water due to the water used for hydration of cement. So the cement hydration, when it occurs and it needs water, so that water is taken from other places. Okay, so that results into autogenous shrinkage. So it may occur even if no moisture movement or from concrete is allowed, and it is very small. It ranges from 50 into 10 to the power minus 6 to 100 into 10 to the power minus 6, the strain value. And this is an example. Second is the plastic shrinkage. Okay, so that is one of the most common shrinkages. Okay, so that is the shrinkage which occurs due to the loss of water due to evaporation from the concrete surface, or suction or removal of water by dry concrete below. So when the cement paste is in plastic state, uh, it undergoes volumetric contraction, and this is termed as your plastic shrinkage. So plastic state is basically the workable state. Okay, so it undergoes volumetric contraction, and this is termed as plastic shrinkage. Contraction induces tensile stress on the surface of layers which are restrained by non-shrinking inner layers. Plastic concrete is weak in tension, and therefore cracks develop on the surface of concrete, because concrete is always weak in tension. Okay, so this is example of plastic shrinkage. Third is drying shrinkage. So drying shrinkage occurs when there is withdrawal of water from hardened concrete which are stored or placed in unsaturated air. So when that air has less humidity or it is unsaturated, then the drying shrinkage occurs. A part of this deformation is reversible. There is 40 to 70% is reversible. That is when the water again comes back, or the air is again saturated back, so it can again swell. Okay, so when concrete dried to air is placed in water at higher humidity, it swells due to absorption of water by the cement paste, and it depends upon the age of concrete. Okay, so this is an example of drying shrinkage. And the last one is the carbonation shrinkage. Carbonation shrinkage occurs due to reaction of atmospheric CO2 with the hydrated cement. So in presence of moisture, CO2 forms carbonic acid, which reacts with CaOH2 to form calcium carbonate. and this results into contraction of concrete and is termed as carbonation shrinkage, and it depends upon permeability of concrete, moisture content, carbon dioxide content, and relative humidity of air. So this is an example of carbonation shrinkage. So what are the various factors, okay, which are influencing shrinkage? So the various factors influencing shrinkage are rate of evaporation, air temperature, relative humidity of air, wind speed, concrete temperature, water cement ratio, volume and fineness of cement, volume and strength of aggregates, volume or exposed surface area, and time or age of concrete. So these are some of the factors which influences shrinkage. So how to provide resistance to shrinkage? So firstly, the most important is proper curing of concrete, and the second is prevention of loss of water due to evaporation. Okay, so for achieving that loss of so for preventing of loss of water due to evaporation, if you have seen, we basically provide various type of gunny bags and jute bags. Okay, we place them weighted jute bags in the concrete structures, okay, after casting. Okay, and there is also some plastic layers. Okay, I forgot the actual name, so some layers are provided, so that basically resists the removal of water from inside the concrete. Okay, or the bleeding to occur, it removes the bleeding process. So then let us go to the next important topic, that is the creep. Okay, so creep of concrete. So what is creep basically? So creep is basically the time dependent deformation. Okay, so deformation or increase in strain under a sustained constant stress, and uh, some amount of creep is reversible and the remaining is permanent deformation. So we will see the figure, we will see the how the creep behavior occurs in the way, with the help of a figure. And it is expressed as a linear strain millimeter per millimeter, generally ranges from 15 to 10 to the power minus 6 to 2800 into 10 to the power minus 6 strain. So this is a creep, okay, in concrete. So this is the figure I'm talking about. So it is a deformation of hardened concrete. If you see, initially there is elastic deformation, that means it is recoverable. Okay, so that is initially, like it is instantaneous elastic deformation. But as time progresses by, the creep occurs. Okay, so under constant load the creep occurs, okay, due to sustained loading. After, again, after whenever the load is removed, so then there is instant recoverable, instant reduction in deformation. Okay, so that is basically the elastic recovery, and then that is also instantaneous. Okay, and again, as time passes by, there is a small amount of plastic recovery. Okay, so but after that, even after that there is some permanent deformation remaining. So that is basically the deformation behavior of creep inside concrete. Okay, so this is a very important diagram. And then there is typical creep curve of concrete. So if you see, there is initial strain, okay, and then that is the elastic strain. And then after that, basically the creep occurs. Here basically two graphs are shown. One is at low temperature and one is high temperature. So there is one, firstly the primary creep, secondly the secondary creep, and thirdly the tertiary creep. Okay, so that is basically whenever the like this during the change of these are basically the inflection points. Okay, when the curve shapes its pattern. Okay, so from concave it becomes convex. Okay, so from convex it becomes concave, and it again changes. So that is the inflection points. So based on those, there we can term those graphs as primary creep, secondary creep, and tertiary creep, the portions. And this is the low temperature creep curve, and this is the high temperature creep curve, and finally fracture occurs. Okay, and it is under load, constant load. So the various factors influencing creep of concrete are volume and strength of aggregates, volume of cement, water cement ratio, strength of aggregate, relative humidity of air, temperature, time or age of concrete. Okay, so these are some of the factors influencing creep. And your this one, the effects of creep of concrete. So it results in increased deflections of structural members like beams, slabs. In concrete columns, deflection increases due to creep, resulting into buckling. In tall buildings, differential creep between inner and outer columns may cause movement and cracking of joints or partition walls. In mass concrete, creep may cause cracking when concrete undergoes differential or cyclic temperature changes. Loss of pre-stress in pre-stress concrete members. Okay, so these are the effects of some bad effects of creep of concrete. Okay, so if we summarize this lecture, so we basically talked about the other distresses in concrete. Firstly, we talked about freezing and thawing, its causes, effects, and the resistance, and also effect of air entrainment. Secondly, we talked about thermal effect in concrete. Thirdly, shrinkage in concrete, where we studied about types, factors, and its resistance. And lastly, we talked about creep of concrete, that is factors influencing creep and effect of creep. So the next lecture we will be going into load associated distresses. So here we will cover the following concepts. Firstly, the effect of loads on structural components, and secondly, location of cracks on structural members. So if we see this figure, this is a very good figure. So it is showing the development of stresses at different locations due to application of loads. So if we represent compressive stress with C, and T represents tensile stress, S represents shear stress. Okay. So if you see here, there are two supports. Okay, so in between the supports, if we see basically under live loads, the beam. Okay, so if we say this is a beam, so and this or the road basically, so it basically sags. Okay, the sagging happens. So sagging means the upper part will be in compression and the lower part will be in tension. Okay, and also there will be shear forces, that is due to the sliding failure. Okay, and your that is happening in between the supports. But if we go to the end support, okay, and if we go to the, if we see the region between the support and the free end, and if there is live load, so the process is opposite. Okay, so the above, so it will be basically in hogging. So it will be like this. Okay, like this. So here the upper portion will be in tension and lower portion under compression. So that is the difference between in between supports and beyond the support. And if we talk about moving loads, one interesting part is there will be no compression, only tension. Okay, so tension is both okay here, but there is no compression here. Only compression is in live loads because it is moving. Okay, so these are some of the changes. And because this is a support and these are the columns, so it will be under compression. And this is the impact load basically. So it is impact because uh, like the vehicle is moving. Okay, so it is like the load will be for a particular very particular limited amount of time. Okay, so that is an impact. And beyond the, if we see, if we say this is the ground. Okay, so be, below the ground there will be dead loads. And this, if this is the support or column, okay, and this is the soil, say for example, so there will be shear again. Okay, or any if this is the even the base of the structure, so it will have shear effects. Okay, in the adjacent faces. Okay, in the end faces adjacent to it, it will have shear. Okay, shear stresses. So this picture has been taken from this book literature. So similarly, if we talk about simply supported beam, okay, so again, if we talk, this is a simply say this is a simply supported beam, and there are UDL, universally distributed load, uniformly distributed load. So the beam will sag. Okay, and because of sagging, the upper portion will be in compression zone and the lower portion will be in tension zone. And if we take a face, okay, a section, cut a section here, so we will see that below, because it is in tension below part, so tension, we will see that tension is maximum here. Okay, and that is resulting in a flexure. Okay, flexure crack. Okay, so this crack, okay, when the crack is perpendicular to the section almost, so it is called flexure. Okay, that also known as tensile cracks. Okay, and the other type of crack which we'll be now seeing in the coming slides, so it will be, one is the shear crack which happens in near the support, and this is the flexure crack. Okay, so tension crack which happens in the bottom at the maximum, at the midspan basically. And if we see here, this has been shown here in a big way, exaggerated way. So the upper part is in compression and lower part is in tension. And because the rebar is also there, it is basically protecting the tension zone, because the rebar is good in tension, whereas the compression is good in, sorry, the concrete is good in compression. Okay. And this is the flexure crack or tensile crack. So this tension flexural crack is formed when the tension in the concrete exceeds the tensile strength of the concrete. Okay, so then the flexural or tensile crack is formed, and this is the part. So this is the location of flexural cracks in simply supported member. So in case of cantilever member, however, it is the opposite. Okay, so here the tensile zone was the lower section. However, here it will be the above section. Okay, because it is it is bending downwards. Okay, so the convexity, so the concave downward it is called downward concave. Okay, so if we see here, the upper portion is in tension and the lower portion is in compression, and this is deflection because of the applied load. So location of maximum tension and possible cracks is this region. Okay, and because of this, the reinforcement has been given above instead of below. So there you can see flexural tension cracks have been generated, and these are also the locations of possible steel corrosion because of the intrusion of chloride ions. Okay, or any other chemicals. And the reinforcing steel must be located in upper portion of member to properly carry tension loads, as we discussed. And the lower part is a concrete in compression on bottom half of slab. Okay, so this is the location of tensile cracks in cantilever member. And if we talk about continuous member, this is the continuous concrete frame, and this is the applied loading. So if you see here the stress reversal occurs. Okay, so stress reversal is basically, if you see, stress it will not be the appropriate word, the stress reversal. So it is basically, it will be alternate, what I wanted to say. So if we see here, because these are the supports, right? So here the hogging negative, this is the region of the negative moment or hogging moment. Okay, and these are the regions of positive moment or sagging moment. So if you see here, the sagging region, the tensile region is below, whereas in the case of hogging region, the tensile region is above. Okay, so negative moment area is above. That's why these are the places of possible tensile cracks in the case of support, whereas in between, the tensile crack region is below. Okay, so location of tensile cracks in continuous member, it is this one. It is opposite. Okay, so it is up and down consequently. Okay, and this is in the case of continuous member. So this is a pictorial representation of the various types of cracks occurring. So in between, as I told you, the flexural cracks occur, which are the tensile cracks, and near the support the shear cracks occur, which is also called the diagonal cracks. Okay, and in between, we have intermediate cracks, which are the combination of both flexure and shear. Okay, so it is a combination of diagonal as well as tensile cracks, or diagonal flexural cracks. Okay, so we can say it that way. So it is a combination of diagonal and tension. Okay, so diagonal tension crack, or shear plus flexural crack. Okay, so if we cut the section also, we can see the shear reinforcements are also present, which we call as stirrup. Okay, in case of beams, and in case of columns we call them as tie bars. Okay, so the stirrups holds the top and bottom sections uh, of the beam together basically. And the flexural shear cracks occur as shown here, and this is the path and location of tension. Oh, and this, if you see, this is the path and location of tension. As I told you, in the sagging area the tension is below, and in the hogging area the tension is moment area, so the tension is above. Okay, as I told you in this picture, we have to put the tensile uh, reinforcements accordingly. So next we come into the column member. So if you see column, so when load is applied, firstly it will undergo elastic shortening, which is recoverable, and then creep shortening. Okay, so this is permanent, and this occurs mainly because of the bulging. Okay, so this bulging results in tensile cracks. So columns, lateral reinforcement or ties resist this bulging effect. So that's why the tie bars are important. Okay, and if we say, so these are the location of tensile cracks in the column. And then if we say about if we say about the slab beam to column joint, so if we, this is the slab, this is the beam, and it is connected to the column. Okay, so if we say here, uh, these are the applied loads, and there is horizontal forces here. So what happens is there is a shear failure occurring sometimes. Okay, so slab and beam are inclined to fall from the supporting column like this, because the shear is like adjacent to the corner sides. Okay, and if we see the shape here, it is diagonal shear. Okay, so it is shear basically diagonally. Okay, shear cracks are obviously diagonal, so diagonal shear cracks. And from top, if you see, there's a this pattern, it can be also called as punching shear crack pattern, because there is subsidence. Okay, so it has come down, okay, abruptly, it is, there is a deformation, vertical deformation, it has subsided. So this is the column, this is the cracking, and because of this it has come down, okay, subsided down. So this is punching. Okay, when it subsides, it's called punching shear crack pattern. And this is the location of, these are the location of shear cracks in slab beam to column joint. Okay, then if we talk about pre-stress concrete, okay, so there we there post tensioning is undergone. Okay, so post tensioning is nothing like the bars, okay, the rebars, they are basically fixed, okay, at the ends, and they are basically tightened. Okay, they're really screwed. Okay, and that results in tension. Okay, so this way the member is the member is strengthened, okay, further strengthened to carry more loads. Okay, however, that can also result into elastic shortening, which can take place after stressing. Okay, stressing is basically it is basically twisted. Okay, so it is screwed. Okay, and that additional shortening occurs as a result of creep and drying shrinkage. So creep can occur, that is due to sustained loading, deformation, and drying shrinkage is basically loss of water due to an unsaturated air environment. And when so basically this happens because of the post tensioning, where the strands are tension, and that basically compresses the concrete. Okay, so providing more strength. Okay, but that can also result in cracks. Okay, location of cracks are shown here, okay, due to stressing. So location of cracks in post tension member. And then if we see here, the cracks generated due to restrained volume change. So here if we see, if we pull this beam from this side and this beam from this side, and a short column is connected here and also here, so because of restraining in volume, okay, restrain, not allowed to change of not allowing the volume change to occur, so there again shear cracks development here. And then if we talk about cylindrical member which is having a overburden load, okay, so say for example this is a pipe. Okay, so pipe, so it is having overburden loads, say soil or any other load is there. And if we talk about the crown is basically the highest point on the inside of the pipe, this point. So if there is crack, okay, and again there is crack in the spring line is basically the horizontal center line of the pipe. Okay, so because it has deformed, okay, pipe deforms under load, this spring line has come down. Ideally it should be like this. Okay, so it should have been like this, but because of higher deformation it has come down. Okay, so these are the location of cracks. Okay, so location of cracks in embedded pipe. Okay, and again there is axisymmetric member, so member which is having the same symmetry. Okay, the symmetry is in a constant axis. So if here we have fluid loading, okay, so so this is a cylinder, and inside this there is a fluid. Okay, fluid inside it, which is creating, which is exerting stress. Okay, which is exerting say for example hoop stress. Okay, the uh, circumferential stress. Okay, so then tension is created by this loading in the circumference, and that results in the formation of vertical cracks. Okay, so vertical cracks form if horizontal reinforcement has excessive stress levels. Okay, so that will result into vertical cracks development. So location of vertical tensile cracks in cylindrical tank. And so we can summarize this lecture. With this we can summarize, and we can say that in the load associated distresses, we understood the effect of loads on structural components and location of cracks on different types of structural members of RC structures. Okay, reinforced concrete structures. So with this we have completed the lectures for the first week, contents for the first week. Now let us solve a few problems and try to properly understand its application. Okay. So first question: blow up failure of concrete pavement happens due to which reason, which effect? A, abrasion of surface; B, freezing and thawing; C, temperature effect; or D, all of the above. So which is the reason, which is the effect due to which the blow up failure occurs? If you remember, blow up happens due to thermal expansion. Okay, so it is basically the temperature effect. So therefore C, temperature effect, is the correct option. Second question. uh, there are two statements. First statement is high water cement ratio results into high capillary porosity with sufficient strength. And second statement is improper placement of reinforcement results into voids and inadequate strength. So which is the correct option? A, statement 1 is correct, B, statement 2 is correct, C, both of the statements are correct, or D, none of the statements is correct. So if you remember the first statement, so that is basically wrong. Okay, so if you see, actual statement should be high water cement ratio results into high capillary porosity with insufficient strength, because it will because if the porosity is higher, capillary porosity, it will result into insufficient strength, not sufficient strength. So statement 1 is wrong, A is not correct. And then statement 2, improper placement of reinforcement results into voids and inadequate strength, so that is true. So statement 2 is true. Okay, so 1 is false, 2 is true. So both statements are also are correct. C option is not correct. C option is wrong because both of the statements are not correct, and one statement is correct. So none of the statement is also not correct, and none of the statement is correct is also wrong. So the correct option is B. Statement 2 is correct. Okay. So as you can see, B, statement 2 is correct. Third question. Statement 1, acid attack in concrete is prevalent in food processing plants. Statement 2, water with pH is less than 6.5 susceptible to severe acid attack in concrete. So what is true? First statement is correct. Second statement is correct. Both the statements are correct, or none of the statements are correct. So if you remember, acid attack in concrete is prevalent for food processing plants. So first statement is correct. However, if you see here, water with pH less than 4.4 is susceptible to severe attack. Okay, severe acid attack. So it is less than 4.4. 6.5 is only susceptible. Okay, not severe. So it is wrong. Okay, so only first statement is correct. Therefore, A is the correct option. So if you see, accepted answer is A. Okay, statement 1 is correct, is the right option. Fourth question. Due to the presence of carbonic acid, the concrete structure is deteriorated by A, calcium sulfate precipitate; B, calcium nitrate; C, calcium carbonate; or D, none of this. So which is the correct option? So if you remember these equations, the carbonic acid results, like it combines with calcium hydroxide and calcium carbonate to form calcium carbonate and calcium bicarbonate. So therefore, bicarbonate is not here, so correct option will be calcium carbonate. So C is the correct option. Fifth question. Statement 1, hardened concrete is susceptible to sulfate attack. Statement 2, during sulfate attack, concrete is damaged due to delayed attringite formation. A, statement 1 is correct, B, 2 is correct, C, both statements correct, D, none statements correct. So which is the correct option? So this delayed attringite formation, if you remember, it happens in internal sulfate attack. Okay, so statement 2 is correct. Okay, because it is a type of sulfate attack. And first statement, hardened concrete is susceptible to sulfate attack. So that is also true. So if you see, it is susceptible to sulfate attack, and during sulfate attack, concrete is damaged due to delayed attringite formation. So both are correct. So C is the correct option. Okay, both the statements are correct. Sixth question. Statement 1, during alkali silicate reaction, expansion happens due to the precipitation of brucite in confined spaces. Statement 2, during alkali carbonate reaction, expansion happens due to expansive clay particles or microscopic quartz particles present within carbonate mineral. So one, which is the correct option? 1 is correct, 2 is correct, both correct, or none correct. Okay. So if you remember, the first statement is actually not correct. Okay, it is not. This precipitation of brucite in confined spaces happens in alkali carbonate reaction. Okay, so in alkali silica reaction, the expansion primarily occurs due to the formation of a gel-like substance called alkali silica gel, which swells when it absorbs water from the surrounding concrete. So not from the precipitation of brucite. Okay, so the expansion occurs from the swelling of this one gel-like substance Okay, alkali silica gel, not precipitation of brucite. So one is not correct, but the second is correct. Okay, alkali carbonate reaction expansion happens due to expansive clay particles or microscopic quartz particles present within carbonate mineral. So two is correct. So B statement 2 is correct is the right option. So B statement 2 is correct. Okay, so this is the correct answer. Seventh question. Statement 1. Freezing and thawing depends upon the degree of saturation and the pore structure of cement paste. Statement 2. Freezing is taking place mostly in gel pores. Capillary pores are too small for freezing. So which is correct? 1 is correct, 2 is correct, all correct, or no correct? If you remember, freezing and thawing, it depends upon the degree of saturation. So lesser, ideally it should be less than 80 to 90%. Okay, and the pore structure of cement paste is important. So here comes the importance of air entraining agents. Okay, so one first statement is correct. This statement is not correct. Okay, so if you may remember, I also discussed like the capillary pores. Okay, so they are greater. Okay, so they are greater. It ranges from 3 nanometer to 30 micrometer, and gel pores are lesser than 3 nanometer. So gel pores are too small for freezing. Okay, so freezing is taking place mostly in capillary pores. Okay, gel pores are too small for freezing. So 2 is incorrect. So therefore, A statement 1 is correct. Okay, so this is the correct. A is the correct option. So most freezing takes place in capillary pores, gel pores too small for freezing. So accepted answer is A. Okay. Next question. Effects of freezing and thawing are A. Breaking down of pore structure. B. Pop out. C. Surface scaling. Or D. All of the above. Which is the correct option. So if you remember, we studied in this slide the effect of freezing and thawing. So this results in the repeated cycles of freezing and thawing results in disintegration of pore structure, that is breaking down of pore structure. So A is correct. It also results in because of this gradual disintegration, it results in pop out. So B is also correct, and surface scaling. Okay, so C is also correct. So all are correct. So D, all of the above are correct. So as you can see, D, all of the above are correct. Ninth question. Statement 1. Shrinkage in concrete is non-load associated deformation in concrete. Statement 2. Carbonation shrinkage occurs due to reaction of atmospheric CO2 with the hydrated cement. So which is the correct option? 1 is correct, 2 correct, all correct, no correct. So if you remember, shrinkage in concrete is actually a non-load associated deformation, okay, which is related to the loss of water, okay. So resulting in volume contraction. Okay, so basically 1 is the correct option. Okay, shrinkage in concrete is non-load associated deformation in concrete, and carbonation concrete, as the name suggests, it occurs when the atmospheric CO2 reacts with hydrated cement. So 2 is also correct. Okay, carbonation shrinkage occurs due to reaction of atmospheric CO2 with the hydrated cement. So C, both the statements are correct option. Correct. Okay, so C is the correct option. As you can see, C, both the statements are correct, is the right option. And the last question, question number 10. Plastic shrinkage is caused by loss of water due to what? A. From the water used for hydration of cement. B. Due to evaporation from the concrete surface. C. Due to withdrawal of water from hardened concrete stored or placed in unsaturated air. Or D. All of the above. So if you remember, the water, when the loss of water is due to the use of water, when the loss of water is caused from the water used for hydration of cement, so that is basically, it is called as autogenous shrinkage. Okay, if you remember, so that is, so A is not correct. Then if we talk about C, so when the loss of water is due to withdrawal of water from hardened concrete which is stored or placed in unsaturated air, so that is basically dry shrinkage. Okay, so that is not plastic, so C is also not correct. But if we see loss of water due to evaporation from the concrete surface, so that is basically the plastic shrinkage. Okay, so during plastic state, when the evaporation, when the loss of water occurs due to the evaporation from the concrete surface, that is basically the plastic uh, shrinkage. Okay, so B is the correct option. So here it is also shown in this slide. So loss of water due to evaporation from the concrete surface, so it is plastic shrinkage. So B is the correct option. Okay, with this, we come to the end of today's problem solving session. So let us meet next week, and we will discuss the second week like course contents first initially, and then we will go with the problem solving. Okay, so with this, I would like to end today's discussion. Thank you.